Alright, so we've discussed the formation of epoxides, and of course we know that an alkene plus MCPBA can give us an epoxide. And there are two faces of that alkene. As of right now, there is no difference between those faces, so we should get a pair of enantiomers in this reaction, and we should get a 50-50 ratio of these enantiomers because there's equal likelihood of the epoxide forming on either side of that alkene. But what if we want only one enantiomer? What if we want to favor just this one that I've underlined? In that case, we need to use a chiral catalyst to produce a chiral environment where that enantiomer is favored over the other. So essentially we want to favor one side of the alkene over the other. And in this case, of course, we'd want to favor the top face of the alkene coming in from in front of the screen rather than behind the screen. And that way we could get an unequal distribution of these enantiomers. Another way to think about this chiral environment is to think about your left hand and how it can tell the difference between the left and the right glove. Right? The left glove fits on your left hand perfectly. The right glove does not. And I'm sure you remember a time when you were a little kid, you put the right glove on your left hand by accident. It sort of fits on, but it feels kind of weird, and your hand doesn't work as well as it would with the left glove on it. Your hand is the chiral environment, and the two gloves are the two enantiomers, and your hand can distinguish between them and essentially make a chiral environment that can produce or distinguish between these two, and thus we can favor one of these enantiomers over the other. So how do we use a chiral catalyst? Well, this reaction works with allyl alcohols or allylic alcohols. And this was developed by K. Barry Sharpless, who won the Nobel Prize in 2001 for this chemistry. So we can take an allylic alcohol, and of course an allylic alcohol doesn't have to have this methyl group here, so let me erase that. Any alcohol that's on a CH2 that's next to an alkene is an allylic alcohol. What we're going to use then is titanium tetraisopropoxide, and we're going to use diethyl tartrate. Which will give us our chiral environment. So this is plus diethyl tartrate. And we could also use minus. Of course, minus has just the opposite stereochemistry at these two chirality centers. So we can use either the plus or the minus, and sometimes we abbreviate that DET, so it's a little easier to write out, a little easier to describe to people. So we mix our titanium tetraisopropoxide with either plus DET or minus DET, and some oxidizing agent that can provide the oxygen in our epoxide, and that's going to be set up like this. There's our allylic alcohol. Here's our oxidizing agent, T-butyl peroxide. Here's the titanium isopropoxide, and we're going to use plus DET in this case, and we're going to produce this version of the epoxide. That enantiomer. And this would be 2s, 3s, 2, 3 epoxy, 1 hexanol. And we get this in 99% EE, 98% EE, excuse me. Which means we have 99% of this enantiomer and 1% of the other enantiomer, which I'm not going to draw. So we get very high EE in this case. So how do we know that we got the 2s, 3s version? Well, that comes from running the reaction. So once we've run the reaction with plus DET or minus DET a few times, we can start to generate a model that will allow us to predict which enantiomer is favored. And so the model that Dr. Sharpless developed involves using an image like this, where we have a generic allyl alcohol and we sort of put this in a plane. You can pretend that it's in the plane of your screen. It's on the plane of my iPad right here as I make this recording. And we found that if we orient our allylic alcohol in this manner with the OH group up to the right, we can then predict that plus DET will add the epoxide above the plane, so coming in from your perspective onto the screen. And if we use minus DET, we add the epoxide below the screen, so coming in from below the table or behind your computer screen, however you're observing this video. And so now with this model, we can now predict the outcome. So let's look at the previous reaction again. Remember that we used this this allylic alcohol. And in this case, let's just use minus DET and T-butyl hydroperoxide and the titanium tetraisopropoxide. And now we can use this model here to predict where does the epoxide go. Does it make a ring pointed towards you, with the O pointed towards you, or is the ring going to project back below the plane of this screen? So what I'm going to do then is to redraw my allylic alcohol so that the alkene is oriented in the same fashion as this alkene, and my allylic portion, the alcohol portion, is in the upper right orientation. So let's see, that's going to look like this here. And then I have 3 carbons that way. So now my allylic alcohol is oriented according to the model. I am using minus DET in this case, so I know that I'm going to add my epoxide below the plane of the page or the screen, and so that would look like that. So I could draw my product like that, and that would be totally fine. We understand what the stereochemistry of these two stereocenters are, right? The O group, the epoxide, is projecting into the screen, whereas everything else is within the plane or coming out of the plane. We could also draw it this way. So now I'm pretending that the plane is essentially this red line perpendicular to the screen. And if I'm going to then orient my molecule like this, I would have the allylic alcohol is projecting towards you within that plane defined by the red dashed line. Remember, this plane is perpendicular. And then the other group is projecting away from you. And then I could fill it in by having a hydrogen here and a hydrogen here if I wanted to. And in this way, both this molecule and this molecule are identical. They have the same stereochemistry at these carbons, and we can use then this model now to predict the effect of using plus DET or minus DET on any allylic alcohol. Unfortunately, this doesn't work for just any random alkene. We must have the allylic alcohol. But as you can see, this is pretty powerful chemistry, and that's why it won a Nobel Prize a few years ago.